But not really. I just don't know what the general meeting is, so I don't know if we'll go to that.
All right, everybody. Next up, we have William Buston, who will be presenting using 3D printing and CAD to design a custom recreational terminal device for a transradial amputee.
Thanks. So yeah, as Warren said, I just wanted to do a quick presentation on a bit of a journey that we went on, developing a transradial paddleboard terminal device. So we had a patient present who wanted to paddleboard, and we had figured we would just go on TRS and order a paddleboard terminal device. And so we searched through TRS, and there was kayak specific, there was all kinds of different devices, but there was actually nothing for paddle boarding. And so I Googled it until I could Google no more, and still nothing. So we decided that we would just make something in-house. So paddleboarding is, I'm sure everybody's familiar with it by now, but it uses a pretty specific paddle. It's kind of like a canoe paddle, except for that it has a longer shaft. It has a standard kind of ergonomic T-handle top, and a paddle on the bottom that's similar to a kayak, but there's a slight angle to it. But other than that, it's pretty standard. And sorry about that. And this particular patient is a left transradial amputee. So that posed some specific problems as far as trying to paddle. And we had talked about possibly using a conventional body-powered prosthesis with a volunteer opening cable, but he did not want a harness. He wanted something that he could click in to his arm. And after thinking about it for a while, we realized that due to the nature of paddling, that the time that he needed to release it and use his body power to open up the hand wouldn't work anyway, because that needs to happen back here as opposed to up front. So we decided to go ahead and create something. So initially what popped into my mind was to use something that was already out there. And up on the screen, you'll see that there's a couple TRS activity-specific terminal devices for, I believe, volleyball or basketball. And I think they're made out of urethane as well. And they would be pretty effective in paddling on one side for him. So he's a left, so he has no use of this arm. And if he had one of those devices, it would definitely accomplish paddling on this side, steering left or propelling himself forward. But when it comes to switching sides, he'd have no way of holding on to this paddle. So what we decided to do, or what I thought of doing initially, was just creating some sort of C-clip that would go between something like a terminal device like this and the prosthesis that would just allow the paddle to pop into and hold it so that he could then transfer his hands. So you can imagine he's paddling, right? And then going to this side is pretty easy. And he just pops it out, and then he can paddle like this. But he has no ability to grip here. And so we needed to create something that would A, hold the paddle securely enough so that it wouldn't slide down when he switched sides, but would also be strong enough to take some force and propel himself through the water. So then I had two uncles come visit me in Kelowna from Toronto, and one of them, his name is Serkan, and he has a Bachelor of Industrial Design, NIT, and he is very skilled with CAD and 3D printing. He has 1 million printers, and he joined us right when we were just starting this project, and he really wanted to go ahead and do this with additive manufacturing and CAD. And so I said, okay. I was really dead set on making something like you had seen. We've done a lot of custom terminal devices and adaptations for orthotics using urethane and just hand making molds and using injection processes. And I knew I could accomplish what I needed to do using those methods. And in hindsight, it probably actually would have been faster. But we decided to go down the modern road. So that brought us to our first kind of prototypes. And this was actually the very first one that we made. I can pass this around. Actually, I'll pass this around. And he didn't bring his printers with him, so we just had this little mini printer that I had with a very small print volume. And so what we did is we printed all these little parts and crudely epoxied them together at the angles that we thought would be correct. And it has essentially two parts to it. There's the cup on the top, and then there's the C-clamp on the side. And I'll kind of just show you. We initially printed everything on a PLA just because it was really quick, but there's the C-clip, and then there's the cup on top. And so we just printed all of these off individually and glued them together. And then this patient likes to use Hosmer, I believe they're HD quick disconnect wrist units on a lot of his recreational prostheses. And so we just kind of adapted and printed this so that it would, we could use a threaded rod to a wrist adapter, and that's how we would connect it to the prosthesis. So I'll pass this one around to you. Our final design that we used was PLA, and I think this was it here actually, and it worked quite well. We had incorporated, you can see there, little kind of spring mechanisms. Why does it keep doing that? And that would kind of allow the shaft to pop in and out. And we figured that if we angled this C-clip at a different angle, that the mechanical holding of it would grip the paddle enough to hold it up during transfer in the hands. But it quickly became apparent that wasn't going to work, and it started sliding through. And the tighter we made it, meant the harder it was to get in. So then what we did is we created some slots on the side that would allow us to silicone glue in some silicone sheeting, and that would create friction enough to hold it up. And it seemed to work quite well. Again, this is our final design. I can pass that one around. And once we had the design perfected in our minds, we always had the goal of printing it off with a resin. Circon felt that resin would probably be the best material for it. There's a lot of resins that would be strong enough to do the job and be impact resistant enough to withstand other forces put on it. And so we printed up one out of resin, and before this one that's up there. And as soon as we did that, it looked good, except for that the ABS leg resin that we started using and the springs that we had put on the C snapped immediately as soon as I put it onto the shaft. So we fixed that one around. So then we decided to alter the design and create kind of like nipples essentially on the entrance to the C-clamp that would achieve the same kind of function and allow us to, and it would also keep the print in one piece, which we kind of felt was important. And so he printed them larger than what's on there, and I just went into the grinding room and with the paddle and just kept grinding them down until it snapped in and out. And it really seemed to work quite well.
Did you take it out of the depth of it in the back, or did you you wouldn't do the front, you'd do the
so
back depth there?
It was the sides there, so they actually kind of curled in a bit, and I'll show you this one. Yeah, this is the one actually that we used. That's the one that's up on the screen that we ground down, and it's the inside ledges that we ground down, and it really seemed to work quite well. And that's a picture of his recreational prosthesis that we kind of made for this arm and another activity, and it just kind of shows the paddleboard attachment relative to the wrist unit, and you can see, get a good idea of how it works there. And then here's it working. So this was one of our first, this actually was our first actual patient trial with it. And it was one of the initial designs with the angles that were right, that was made out of PLA. And you can see he's paddling downward, clicking in, and he's transferring quite well. And we made a few design changes, and just the small ones. We opened up the opening on the attachment at the very top section here, just to allow more range of motion with the paddle. And that's him demoing it right there, which is awesome. So we're just simulating him being in the water, and Amanda's just giving him some advice on how to effectively transfer it. And we won. It was perfect. We were so happy. So after this was actually a couple months ago, we decided to made plans to go paddleboarding in the water and test it out in the real world. And we had tried to get together for about 4 or 5 times. And he's really busy and I'm really busy, and it never quite materialized. But then about a week and a half ago, or a week ago, we had a window of opportunity, and right before he flew out to here and I flew back to Ontario, I rode my bike like a madman down to the lake, and he brought his paddleboard down, and I was just gonna take 2 videos in 2 planes just to show how it works. And so we helped him get his paddleboard in the water. He went out 30 feet into the lake and was sitting on his paddleboard. And if anybody's ever paddleboarded, the way you stand up is you kind of lean forward and push up, and kind of in one motion put all your weight on your arms to kind of jump up onto your paddleboard. And as soon as he did that, it failed. And so that was so disappointing. We were just shocked, and I was unprepared to go in the water, but I stripped down and dove down 25 feet and found the parts in the bottom of the lake. And then we realized that this whole time our design had been focused solely on paddling, but not on the other forces that would be on it, like standing up and so I literally ran back to work, grabbed my stuff, hopped on a plane, and joined Sir Ken in Toronto, where he got on Fusion 360 and redesigned the attachment point between the threaded rod and the terminal device to beef it up. He printed it off in PLA and has been he printed it off in PETG, and he's been trying to break it ever since, just to see if it would work. And are we ever running out of time? Okay. And so that seemed to be great. He could not break it, so we started researching resins, and we found the toughest resin in the world, and this guy printed up 30 different lug nut sockets out of resin, and then used a torque wrench and simulated torquing them on a bolt with a torque wrench, and then recorded when it failed. And this Create ToughX resin failed at about 90-something foot-pounds of torque, which is more than you tighten some cars' lug nuts. And it's our final, I hope, device is getting printed with it as we speak. So that was kind of our journey, and I wish I had a video in the water to show you. But I just wanted to say thanks to Sir Ken, because I could never have done this on my own, and Mateus and Amanda and Curtis for being a guinea pig.
That's great. Thanks for attending. Please make your way to the